Welcome to part 2 of the Beginner's Guide to Composites. In this video, you're going to see several of the techniques that are used for making carbon fiber or fiberglass parts. Each of these techniques have essentially three things in common. One, you need some kind of a tool or a mold. That's what gives the part its shape. Number two, you need to wet out the fabric somehow, saturate the fibers with the resin. And number three, you need to stick the plies together and ideally have some way to compact them so that they all are uniform and they don't peel apart easily. Look for those three things in each of these techniques. Perhaps the most basic method of layup is contact layup. There's no vacuum, there's no bladder, there's no autoclave, nothing to compress the plies together. All you're doing is you're brushing or rolling epoxy into the plies in the mold and then letting it cure when exposed to the open air. Without that compaction, you don't get as strong of a part. You have more resin in your layup, and so it's heavier, it's not quite as strong, the plies will peel apart a little bit easier, but that doesn't mean it's not a viable method of making a part. In fact, there have been entire airplanes built with nothing but contact layup. This rattan Long Easy was designed in the 1970s to be built entirely out of fiberglass, using nothing but a brush and basically a squeegee made out of a plastic lid. The canard, the fuselage, the wings, all of the structure of this airplane was designed to be built with nothing but contact layup, no vacuum pump. And this airplane is still, even today, one of the most fuel-efficient small airplanes in the entire world. So can you make a quality composite part without a vacuum pump? Yeah, you can. The second technique is vacuum bagging. I want you to imagine that you had a 10-inch by 10-inch piece of carbon fiber you wanted to lay up. To compact the plies, you put a book on top of it. The book weighs 5 pounds. Now that 10-inch by 10-inch area has 100 square inches of area, 10 times 10. So if you put that 5-pound book on top of it, the pressure that you're putting on it is 5 pounds divided by 100 square inches, or 0.05 pounds per square inch. Now what if instead you put that layup inside of a vacuum bag, you suck all the air out, and now you have atmospheric pressure pushing down on it. And atmospheric pressure is about 14 psi at sea level. 14 psi versus 0.05 psi. That's a big difference. In fact, to get the same level of compaction as you could get with a vacuum bag, you'd have to stack 280 books on top of it. Not exactly practical. That's why people use vacuum bags with composites, is to compact those layers together in a way you can't do by just putting weights on it. The other advantage is that if you have a curved part, it's really hard to put weights on the sides of your mold. A vacuum bag sucks it down to the sides and you get even pressure all the way around that mold. The result is a lighter and stronger part. For vacuum bagging, it requires a few extra materials, however. First, you'll usually put down a peel ply. You don't have to put the peel ply down, but what it's for is after the layup is done, you can leave it on there and it'll protect the carbon fiber from the oils of your fingers while you're handling it or from whatever else until you're ready to bond something to that, if you need to bond something to it later. So if you're gluing another part to this part afterwards, if you have that peel ply on there, you can just peel it off and you have a surface that's ready to bond to without doing any additional prep work. After the peel ply, you put down what's called a bleeder. This is a thin film of plastic that's been perforated with holes all across the entire area. And what it does is it provides a barrier between your layup and your breather, so the breather doesn't stick to the layup. But it also allows resin to pass through, so you're pulling the excess resin out of your layup and you get that lighter part. The breather serves two functions. First of all, it soaks up the excess resin. And second of all, without the breather, sometimes the plastic will close itself off to a section of your part, and then that section of the part won't see full vacuum. You don't get the compaction you need, the part might have to be scrapped. So the second function of the breather is to spread the vacuum across the entire part so you have full vacuum everywhere. And then last is the bagging film. It's just a non-permeable film that gets laid over the entire thing to seal it all off. And to seal the edges, you usually will use what's called a BST or a bag sealant tape. It's a really sticky tape that you put all around the edges and it sticks to the bag and it seals the whole thing off. Vacuum bagging can give you good compaction, but bladder molding can give you even better compaction in your layup. We mentioned before that a full vacuum at sea level gives you 14 psi of compression all the way around your part. Well, with a bladder, you can go even higher because you get to control how much pressure you put on that part. Bladder molding is typically used for long, slender, or round objects. This is the technique that I use to make the fuselages for my gliders. And I ramp the pressure up to 60 psi, 4 times higher than I can get with just a vacuum bag. And it's noticeably easier to get a really shiny surface finish. And what's more, it compacts the plies even more, so I have a really good bond from one ply to another, and you get a really strong part. For long skinny molds like this, I use Qualatex balloons for my bladders. But there are companies out there that make custom silicone bladders that allow you to mold parts in almost any shape that you can imagine. An autoclave works on the same principle as the bladder. In other words, it's great to have 14 psi of pressure, but if you can ramp that pressure up even higher, you get a better part. So what an autoclave does is a little bit different than a bladder though. With an autoclave, you'll still vacuum bag the part, but then you put the entire part with the mold into a pressure chamber, and then you can ramp the pressure up inside the chamber, usually to about 60 psi. The combination of sucking all the extra air out of the layup and then adding pressure on the outside gives you a very good compaction, and it practically eliminates any bubbles that might be in the layup. So you get a much shinier, smoother finish on the surface and a stronger laminate as a result. In big aerospace companies, it's not uncommon to see autoclaves that are 40 feet long and 20 feet in diameter. Massive autoclaves for making huge airplane parts. And autoclaves are expensive, so you don't usually see them in a home shop. Vacuum infusion is one of the best ways to get a really good surface finish on your part. The principle behind vacuum infusion is that you put all the parts in the mold, all the plies in the mold dry. Then you have 2 ports inside the mold, one where you're pulling the vacuum, sucking all the air out, and then another port on the other side of the mold that lets the epoxy flow into the layup. So as you're sucking the air out, you're also sucking the epoxy in, and it flows from one side of the layup to the other, and you get a very low porosity part. This is great if you want really pretty parts. However, they tend to be a little bit heavier. Vacuum infusion is all about getting the setup right. If you get the setup right and you're meticulous about that, then the infusion will probably go well. Vacuum infusion can take a little bit of practice and a little bit of experimentation to get it right, and it's a little different for every part, but the principles are the same. Make sure that you have all of your area getting saturated with epoxy before it reaches the vacuum port. But as long as you prepare well, you can get great looking parts from it. And the last technique that I want to talk about is filament winding. In filament winding, instead of having a female mold that you're putting plies into, you have a mandrel that you're putting your carbon fiber around. And they call it winding because it's just like winding thread onto a spool. You'll have some kind of a robotic head that lets the carbon fiber tow out as it moves across the part. And you can program it to move at different speeds to control the angle that those fibers are winding at, so you can orient those fibers to the optimum direction. One of the nice things about filament winding is that it's stretching the fibers as it puts them down. It puts them down with tension, and so you get a very uniform and strong part as a result of it. Filament winding is used all the time for tanks and things that have to hold pressure. You can make a much lighter tank out of carbon fiber than you can out of steel or aluminum. And filament wound carbon fiber is the material of choice for rocket motor cases in a lot of applications. And finally, a word about cutting and trimming composites. First of all, let's talk about what not to do. Do not use a blade that's designed for cutting wood or metal. Those blades cut what they're meant for really well, but they will not cut composites terribly well. And what's more, carbon fiber is extremely abrasive. And so after just a couple of cuts, your saw blade is not going to cut anything else ever again. It will dull the blade that fast. They make bandsaw blades specifically for cutting carbon fiber. They're usually some kind of a diamond abrasive. They tend to be kind of expensive though, so in my shop instead what I use is an abrasive cutoff disc on a Dremel tool. These discs are extremely inexpensive and they last a long time. Just make sure that you get a Dremel tool with a sealed switch. The first one that I bought didn't have a sealed switch, and it died after about a year of use, and here's why. Carbon fiber conducts electricity extremely well, so all that carbon dust got down into the switch, completely buggered up the electronics. It was ruined. Fortunately, Dremel stands by their products and they honored their warranty. Not only did they send me a replacement, they upgraded me to a better model that had a sealed switch. And this model, I've been using it for years and I've never had a single problem with it. I'll put a link in the resources to the one that I use, that I stand by, and I will keep in my shop forever. In bigger shops, it's common to see air tools used instead of electronics, specifically for that reason, because carbon fiber conducts electricity. Still, I've been using this one for years and I have not had a single problem with it. If your laminate is thin enough, usually 2 plies or less, you can get away with cutting it with just a pair of good scissors. And whether you're using scissors, a Dremel tool, or a bandsaw, I like to cut a little bit outside my final trim line and then take some sandpaper and just kiss that edge just enough to get it down to that trim line. That gives you a really clean, crisp edge, much better than you can do by cutting with a power tool. And then lastly, control the dust. Dust will ruin things in your shop. It will ruin computers and electronics in your shop if you let it roam freely about. So control the dust. And one of the best ways to do that is to have a vacuum right there on hand next to your cut, sucking up the dust as it comes out of the part. That way you're controlling the dust at the source and it doesn't have a chance to spread elsewhere. And that's it. Now you should have a pretty good knowledge of what the different types of carbon fiber manufacturing there are and where each one is better than the other. In our next and last video in this series, I'm going to walk you through how to make your own carbon fiber part, how to start your first project, and we're going to make it from one of the beginner starter kits from GorillaCarbons.com. I'll see you then.